Hello everyone, my name is Simon Ganchev and I'm going to present to you the plenary talk entitled Smart Real-Time Recommendation of Mobile Services for the 30th International Conference on Circuit Systems, Signal Processing, Communications and Computers 2021. This talk was prepared in cooperation with my colleagues Professor Zhanlin Ji from North China University of Science and Technology, China, and Professor Odroma from University of Limerick, Ireland. My talk includes 5 parts. After a short introduction, I'm going to present the related work in this area, and then we'll present the elaborated service recommendation framework and the smart service recommendation system developed based on this framework. At the end, conclusions will be drawn. Recommendation systems are vital for consumers for addressing the information overload problem and assisting them in navigation through the vast information oceans as to find the information, item, application, service or thing they need. The goal is to provide them with accurate recommendations as fast as possible. This is a highly dynamic process with the increasing number of items, applications, services and things emerging. The research and development efforts to date have been mostly focused on item recommendations, whereas app recommendations and service recommendations are left behind. In the sub-area of item recommendations, a lot of work has been done ranging from e-commerce, either by recommending items right at the spot, or for online shopping at a retailer website, or for online shopping through a mediator, for instance a video game or a social media, to entertainment domain, for instance recommendation of TV programs, streaming items, photos, music, etc., and even to e-learning domain, for instance by recommending personalized online test questions for students. Some work has been done also in the sub-area of app recommendations. Academic research examples here include recommending mobile apps that other consumers have installed or use frequently in the same location, or mobile apps simply based on their version description. Basically, personalized app recommendations are provided by combining collaborative filtering techniques with mobile apps usage data and by utilizing implicit consumer feedback. Commercial examples include providing a list of similar apps, for instance in the recommendation section of another app used by the consumer, such as Google Play, Apple Store, etc. However, recommendation algorithms used are usually not made public, and in addition there is a forgotten majority problem related to the fact that provided recommendations seem not very effective and not evenly distributed among the existing apps, either due to fraudulent app promotion or manipulation, or no exposure behaviors, which may increase the exposure of some marginalized apps by making these more visible to potential consumers or constraining the exposure of other good apps. A relatively new direction in this regard relates to the Think recommendations within the Internet of Things area, focusing on different application domains such as intelligent transport systems, smart health, smart cities, smart home, etc. ITS examples include computing and dynamically adjusting the optimal car travel paths based on real-time traffic information and in addition generating and sending to drivers precise parking lot guiding suggestions. In the smart health domain, examples include personal health reminders or pushing up-to-date health-related notifications to consumers. Smart city examples include real-time alerts about areas of high pollution and finding the most healthy or secure route to follow by a consumer in order to avoid areas posing particular health or safety risks to them. The smart home examples include homes equipped with motion sensors, monitoring the movements of usually elderly people living there, and a supplementary system assisting them in their daily life activities. The sub-area of service recommendations has attracted great attention in the last few years. The work here ranges from recommending a specific aspect, parameter, feature, component of a single service to recommending a new instance of the same service or completely new service. More sophisticated examples include knowledge-based recommendations for dynamic, runtime, proximity-based service compositions for mobile devices and consumers. However, there is a lack of a global solution applicable to all types of mobile services, as well as many internet services and the newly emerged types of IoT services. For service recommendations, usually brokers are used to assist in collaboration between consumers and service providers and match them through an auction mechanism. In addition, they may provide more comprehensive functionalities such as service packaging and monitoring for matching the requirements of consumers with the service level agreements offered by the providers. Also, multi-attribute negotiation with service providers may be provided by the brokers on behalf of the consumers. To make the right decisions, brokers use either consumer behavior or historical records of consumers or direct consumer experience and feedback, or calculate consumers' aggregated requirements to find an optimized match of this with available service offerings, or use more sophisticated machine learning techniques to better understand consumer preferences. In addition, brokers consider security and trust assurance in service matching and have self-learning ability. The broker approach is also used by the service recommendation framework presented following this talk. The presented service recommendation framework is able to provide each engaged consumer with a contextualized, customized, and personalized list of preferred best mobile service instances. This slide illustrates an application example based on an ongoing voice call service. Let's assume that consumer A wants to call consumer B always in the best possible way, for instance, the cheapest way. The cheapest option, presented in green color here, would be to utilize the voice over IP VoIP technology, for instance by using the mobile app provided by some VoIP provider as to initiate an outgoing call over a free or paid Wi-Fi connection. This Wi-Fi/VoIP option will be the preferable one when consumer B is a friend or a family member, as this involves a minimum cost even though with the lowest quality. However, in doing this, consumer A could still miss an opportunity of using another VoIP service provider who supplies better rates for making a voice call to consumer B. The elaborated smart service recommendation framework can find such opportunity For instance, the existence of a beta VoIP service instance and suggest it in real time to consumer A. The second option, presented in red color, would be to use cellular connection. The high quality, high cost option will be the preferable one when consumer B is a business partner or important client. The situation, however, may change drastically when one or both of the involved consumers is currently in a foreign country due to the associated high roaming cost. In this case, additional and more attractive option presented in orange color here is to use a local SIM card which is on sale in the corresponding foreign country instead of the SIM card provided by the home country's cellular operator. This is the preferable option for making phone calls abroad, especially in countries where the home operator was unable to negotiate better or lower roaming costs for its subscribers. Yet the best option, if a high-quality voice call is required, would be the use of a global SIM card, which in many cases could deliver the lowest cost. The use of another not home SIM card, even in case when it is an embedded SIM, eSIM card, comes with difficulties, however, in finding if that particular card can provide indeed competitive cost for calling that particular consumer B, as this depends also on his or her current location, including the country where she or he is at the moment of the call. All these scenarios can be easily served by the elaborated smart service recommendation framework presented in this talk. The main features of this framework include scalability and efficiency, managing big semantic data in real time, automatically finding the usefulness of available services and recommending the best one to consumers, dynamical provision to consumers of ordered list of ranked services based on consumer, network and service context, adopting a suitable graph database for storing and managing the information about services and consumers as a heterogeneous service network based on a given network schema, and discovering consumers' features, which is accomplished by utilizing the betweenness centrality within the scope of this network, which is a novel approach for consumer profiles generation based on the metapaths concept. The framework facilitates the relationship between service providers and consumers by allowing the latter to specify their demands for services or by guessing these demands on behalf of the consumers. At the end, a personalized, ranked list of top N recommended best service instances is delivered to each consumer by taking into account the current context and consumer preferences as part of the service recommendations personalization process. The four-tier structure of the framework is presented here. The service tier dynamically models services and their attributes as a heterogeneous service network based on the gathered information and following the adopted network schema. The consumer modeling tier extracts profile kernels and provides an index for high-speed data searches in the consumer profile repository. The analysis tier provides an algorithm toolkit to support the HSN analysis and profile kernel discovering by the consumer modeling tier. In the recommendation tier, a recommendation engine recommends the best service instances to consumers. The other task relates to the service popularization. Here, a global ranked list of popular services is provided to all consumers for instance via a wireless billboard channels. For service recommendations personalization task, a hybrid context-aware approach is followed with 3 stages. The first one is pre-filtering, by using contextual information to pre-filter the recommendation candidates. The second stage is semantic recommendation, based on semantic ratings obtained from the knowledge base part to enhance the effectiveness of recommendation. And the third one is post-filtering, based on additional information, for instance, how old or how new is a particular service instance recommended, and the willingness or hesitation of the consumer to use such old or new service instance. Determining the best service instance at any moment for a particular consumer is based on a set of context parameter values categorized in 3 groups: consumer-related C, service-related S, and access network-related N, forming a 3D context space as illustrated on this slide. Consumer context includes physical context, for instance, location, date and time, body position, type of activity and emotional state of the consumer, and even weather conditions such as air quality, pressure, temperature, humidity, light, etc. Also, consumer contents includes social context, for instance, the presence and role of other people around the consumer and their social interaction with him or her, and also interaction media context, for instance, the mobile device used by the consumer, including its current battery status and other operational characteristics, and the type of media that is being utilized and personalized for text, music, images, movies, visualization, etc. Also, model context is part of the consumer context. For instance, the state of mind of the consumer's goals, mood, experience, intentions, social interests, cognitive capabilities, privacy and security concerns, etc. Also included are the upper bounds on the price and the lower bound on the quality of service or quality of experience accepted by the consumer for each particular service. Service context relates to services available on offer, for instance, the service category, type, scope, and other general attributes such as responsiveness, scalability, security, trust, etc. Also, the application initiating the request, the current QoS/QoE index of the service cost, etc. Network context relates to the constraints of the wireless access network currently utilized by the consumer. For instance, the communication channel state information, the network congestion level, the current data usage pattern, the current QoS/QoE index, the cost of using the network, the pricing scheme, etc. Based on the presented framework, a smart service recommendations is elaborated with a modular structure containing 3 domains related to the consumer, web, and cloud, as shown on this slide. In the consumer domain, an ABCNS, is best connected and best served application, runs on the mobile device to visualize to the consumer the best service instances recommended by the system. This app is used also for automatically selecting the best service instances depending on the current context, including in that decision process the consumer's personal profile requirements. In addition, for the service popularization option, the WBC app runs also on the consumer mobile device for receiving and processing the list of new, popular, emerging services created by the corresponding WBC management module. All service descriptions are cached by it for broadcasting on WBC and pushing to the mobile devices. One of the key parts in the web domain is the delivery server, which collects aggregates information about the consumer behavior monitored by the ABCNS app and delivers back recommendations about the best mobile service instances. The recommendation engine is the central one used for uploading the recommendation algorithms to the system and defining or updating the recommendation rules. Through its service description SD retrieval module, it searches for the relevant keywords in the SD index database, facilitated by the consumer profile attributes, the web page attributes database, and real-time bidding system for demand, RTBD, and as a result, an initial service recommendation list is generated. The list is then pushed to the SD ranking module and after computing with the click-through rate CTR module, the final personalized list of top and recommended service instances is generated. This list is sent back to the consumer's ABCNS app via the delivery server and simultaneously is pushed also to the distributed log data real-time collection module. In addition, a globally recommended list of services is generated by the SD ranking module for a global delivery to consumers via the WBC infrastructure. The cloud domain facilitates the storage of consumer data harvested via mobile devices and collected by other means, and based on the analysis of this data, offers predictions as to the applicability and ABCNS suitability of services to the consumers. This domain consists of three main parts: data management platform, DMP, stream computing, and distributed log data real-time collection part. Given the dominance of the Android and iOS operating systems in the market, the development of software applications for these operating systems is primarily targeted in the consumer domain. In the web domain, in the case of having a great number of mobile devices, simultaneously maintaining persistent connections with the delivery server and supporting continuous data collection, the design of this server is a big challenge. This problem has been properly tackled by employing a distributed technique that is able to handle a large number of clients at the same time. In the service recommendation system presented here, Nginx, Redis, and Zookeeper technologies were used to build a distributed server architecture allowing a high level of concurrency of the web server. The web domain contains a distributed Redis cluster and web application. The distributed Redis cluster consists of two layers. At the database layer, a Zookeeper-based cluster is used for distributed operations. To simplify the access to the Redis cluster, a Redis executor was designed with a concurrent hash map algorithm for databases write-read operations. At the service layer, in order to provide a Redis service and a monitoring service for the upper layer, the service governance scheme was elaborated for exploring the services, interfaces, and providing a distributed remote procedure call (RPC) mechanism. For the web application, an RPC mechanism and an MVC structure were elaborated by redesigning the GWT HTML5 struts, and an Nginx load balancer is used to act as a fast connector between the consumer domain and the web domain. A Flume-based distributed message system collects log data and serializes it to the cloud. The distributed Redis cluster at the database layer supports the producer-consumer model. A Redis package was designed with JEDIS operations such as keys, strings, hashes, lists, sets, sorted sets, etc. Within the package, a functional Redis executor interface with one abstract execute method was designed. To achieve a loosely coupled system, a producer-consumer model, serving as a distributed framework for push notification service governance, was utilized for the provision of sync over async and request response messaging functions with an RPC mechanism. The producer registers a service to the zookeeper when a consumer subscribes to that particular service. Then the zookeeper notifies the consumer and the corresponding service is invoked. Besides creating a service access interface and managing the session, a distributed message collecting scheme was also implemented based on Flume. A typical scenario of a log collection provided by Flume involves deploying a Flume agent on each web node, which requires an extra Java virtual machine. So, in the presented Smart Service Recommendation System, this resource-consuming element was replaced by an UCWW sender. A tail cursor monitors the log document. In the cloud domain, a data management platform (DMP) based on three-layer Lambda architecture has been elaborated. The batch layer processes the growing datasets in a distributed big data file system by utilizing MapReduce operations and Hadoop. A number of batch shell scripts were designed for driving the Hive queries in the DMP. The serving layer indexes and exposes the batch views in order to query the system in an ad hoc way and with low latency. The Apache H-based technology was utilized as it offers random and real-time read-write access to the DMP database. The speed layer provides real-time operations on recent data and frequent updates to the serving layer by means of stream processing. The open-source distributed real-time computation Storm technology was utilized here as it is capable of fast data processing at the rate of million tuples per second per node. The data management platform DMP is the key component in the cloud domain. A number of logs need to be recorded on DMP, such as service type, service session start time and end time, and duration, and so on. During this process, supplementary services are loaded on the DMP for consumer profiling and audience targeting. To support data serialization and RPC operations within the Hadoop environment, the Apache Avro technology was employed to provide the scripting languages. The logs are first fetched and published by the Kafka spot with high throughput and in a distributed manner. Then the Storm bot consumes the log topics. After real-time tag analyzing and non-real-time statistics calculation, the output dataset of Storm is published to Kafka, including a number of topics. The data processing is shown on this slide in more detail. To achieve high throughput and low latency, two distributed publish-subscribe Kafka-based modules were designed for data processing and for data subscribing and message storage respectively. The Apache Avro technology was utilized to support data serialization and RPC operations within a Hadoop environment. The Storm bot technology was utilized to consume consumer log topics. As the raw logs in the design DMP are stored in a distributed fashion to achieve high throughput, a Kafka-based distributed publish-subscribe messaging module was designed for use in the data stream part for data processing. The Apache Kafka publish-subscribe messaging platform was chosen as it allows a single Kafka module, a broker, to handle hundreds of megabytes of reads/writes per second from thousands of clients simultaneously. In the query part, another Kafka-based module was designed and used for data subscribing and saving messaging on the disk with ETL batch consumption operations. It uses the commues to fetch available topics and to store them on a Hadoop distributed file system (HDFS), which is a portable file system written in Java for the Hadoop framework. And here I come to the conclusion. The presented, elaborated Smart Service Recommendation System can be used as a platform to assist service providers of any kind to reach valuable targeted consumers by supplying to them in real time an up-to-date list of ranked services to choose from at any location at any moment. In addition, if these services are used via the best available access network, this would help realizing a truly consumer-driven, always best connected and best served ABCNS communication paradigm. Thank you for attention. This plenary talk has emanated from a research conducted with the financial support of the Bulgarian National Science Fund under the grant number KP06IP China/1.